This video is going all the way through 7.5, which deals with solving exponential and logarithmic equations. So in some ways, we've kind of done some of this. We're going to start kind of easy, solving an exponential equation with a common base. So if I ask you to solve 5 to the x to the power equals 125, you can kind of just think through what this might be. And if it's not super apparent, what you can do is you can rewrite 125 as 5 to some power. So this could be like 5 to the x to the power equals 125 is 5 to the third. So then obviously x just has to be 3. And that one wouldn't be so bad because you just know 5 cubed is 125. But for like this one, we can use that same method. So if you have 27 to the power of 3x equals 81, you're going to want to rewrite these with a common base. That base would be 3. So 27 is 3 cubed, and then you're taking that times 3x. 3 cubed is 27 to the power of 3x. That's what that's saying. And 81 is 3 to the fourth power. So now you can just look at the exponents. 3 times 3x equals 4. So 9x equals 4. So x is 4/9. So if you do 27 to the power of 3 times 4, which is 12 over 9, which is like 4 over 3, just to like check your work, you definitely still get 81. So you can always check your work with these two, even if your numbers look kind of funny. This is a 4. We'll try one more. So 4 to the power of 2x plus 1 equals 1024. You can play around with this a little bit, but 1024 is just equal to 4 to the fifth power. And if that's not super obvious to you, you could like break it down or just start dividing and see what you get. But once you rewrite it with a common base, you don't need to bring it all the way down to a base of 2. We could, but we don't need to because now that the bases are both 4, we can just set the exponents equal to each other and solve. So x is equal to 2 when it's all said and done. And then if you kind of think of this the other way, 4 to the fifth power equals 1024. That's what we just said right there. So those are kind of our easier ones. It gets a little trickier when you have a different base, but it's really not so bad as long as you have your calculator with you, because your calculator has the ability to do any base you want. So it's just going to be some calculator work. So if you have 3 to the x to the power equals 17, what you're going to do to get x by itself is you're going to rewrite this in logarithmic form. So you can kind of think you're doing the inverse or you're just rewriting it. We did a lot of practice with this earlier. But what we said was the base is always the base, and then we could kind of do that little swing thing. So you'd have log base 3 of 17 equals x. And boom, we have x by itself. So then I got to get my calculator out. But then all you have to do is you just do that in your calculator. So you press the log button, base 3, put in your base of 17, press enter. You're going to get 2.58. So it's really all calculator work once you have it rewritten. Let's try that with this one too. You have 5 to the power of 2x equals 135. Our base is always our base, so we're going to do log base 5 of 135 equals 2x. And now I'm going to evaluate this. Well, I'll divide by 2. So x is equal to log base 5 of 135 over 2. And then we're going to get a number. So I'll do that right now. Log base 5 of 135 divided by 2 is 1.52. So really you're just rewriting it in exponential form. Now the other option, which you can totally do, and this is going to be a method we might use later on, is you are allowed to do the log of both sides. What this means is if you have 3 to the power of x equals 17, you could do log base 3 of 3x equals log base 3 of 17. And what that does for you is now that we know our properties, we can swing the x out in front. So you get x times log base 3 of 3 equals log base 3 of 17. And then we know that's just 1. Log base 3 of 3 is just 1. So x is equal to log base 3 of 17. So you effectively get to the exact same place. That's why we're not really doing it. But in a later lesson, we might use this method to introduce a log to both sides. So just showing you that you can do that to solve. Okay, let's do one more. You could try this on your own if you wanted to pause the video. So why don't you do that? Give yourself a chance. Try this one out. Use your calculator. Ready, go. Okay, let's do it. Our base is always our base. So we do log base 8 of 26 equals y minus 3. So you get log base 8 of 26, that whole quantity, plus 3 is equal to y. And then you just put all that in the calculator. So log base 8 of 26, and then we'll add 3, and we get 4.57 for y. Done. Okay, so let's just kind of use this with a real world model. So the world's population could be modeled by the equation P equals 6.72 times 1.014 to the power of x, where P is the population in billions of people, x years after 2000. So this was a model that they came up with in the late 90s to model population after the year 2000. So based on this model that they came up with 20 years ago, what would they estimate that the population is in the year 2020? Well, we just need to plug in a value for x, right? So 20 years after 2000 is just 20. So this one's pretty easy, 6.72 times 1.014 to the power of 20. Let's see what we get here, 6.72 times 1.014 to the power of 20. Population 8.87 billion. Now that seems a little high, obviously. And this model was 20 years old, and obviously there's things that have to do with the population that just don't allow it to increase at that high of a rate over time. But just for the sake of argument, let's just have some fun with this. In what year would the world population be about 15 billion people? So here now we're solving for x. So we're going to do 15 equals 6.72 times 1.014 to the power of x. Now before we can rewrite this in log form, we want to get this exponent piece by itself. So we're going to divide by 6.72. So we get 2.232 equals 1.014 to the x power. And now we can rewrite this in log form. The base is always the base. So it's a funny looking base, but the base is just 1.014 of 2.232 equals x. That's just rewriting it in log form. Then we go ahead and put that in our calculator, and let's just see what kind of year we get. 2.232. X is 57.75. So in like the year 2057 to 2058, somewhere in that range, the argument would be that we would have 15 billion people. I have no idea if that's true. Maybe if YouTube's still around, by then we can go back and check in 2057. Who knows? Okay, so to solve logarithmic equations, we're about done. It's the same idea, only now you're going to just rewrite it in exponential form. So if you have log of 2x plus 1 equals 1/2, our base here is 10. Our base is always our base, so we can do our swing. 10 to the 1/2 power equals 2x plus 1. So 10 to the 1/2 power minus 1 equals 2x. And then x is that whole quantity divided by 2. So that's like the square root of 10. However you do it, it doesn't really matter. Square root of 10 minus 1, that whole quantity divided by 2 is about 1.08. So it's the same idea, you're just now rewriting in exponential form. Let's do this one. We have a negative out in front, so we can divide by -1 on both sides. So you got log of 3 minus 2x is equal to +1. Rewrite in exponential form, so this is 10 to the first power equals 3 minus 2x. So subtracting 3, I'm kind of running out of room, sorry. We get 7 equals -2x. So x is equal to 7 over -2, or like -3.5. Either way you want to do that. Same idea, you just rewrite it in exponential form instead of logarithmic form. Last thing we're going to do is we're going to use our properties to solve. So log of x plus 9 plus log of x equals 1. We need to combine this first into one logarithm. So since we're adding logs, we would multiply what's inside. So log of x times x plus 9 equals 1. Our base is 10. So now we'll rewrite it in exponential form. 10 to the first power equals, I'm going to go ahead and distribute x squared plus 9x. Now to solve this equation, this is just 10, so we'll subtract 10. 0 equals x squared plus 9x minus 10. Now we can factor x plus 10 times x minus 1. So x equals -9, or x equals 1. And now when we look at these options, we have to see, do we have any extraneous solutions? And we're going to see at -9, that is an extraneous solution because you can't have a log of a negative number, or even 0. So we don't care about the -9. Our only answer is 1. And if you think about plugging 1 back in, log base 10 of 10 is 1, log of 1 is 0, 1 plus 0 is 1. Done. Last one, log base 10 of 6 minus log base 10 of 3x. Since we are subtracting, that's like division. So this is like log base 10 of 6 over 3x equals -2. So that means 6 over 3x equals 10 to the -2nd power. So now you can solve this however you want. How I like to do this is maybe just write it as a proportion. 10 to the -2nd is 1 over 10 to the 2nd. So 6 over 3x is equal to 1 over 100. Cross multiply. 3x is 600. So x is 200. And we're done. And that wraps us up for all of 7.5.